Thanks to everyone for coming. I'm really excited to be here today. This talk is about measurements of time in astronomy and everything that means. It's about all scales of time and how different time scales actually interact. Okay, so a little bit of context. I'm interested in studying the planets in our galaxy. So to date, we've found almost 4,000 planets outside of our solar system. These are planets that orbit different stars, distant stars, but stars that still reside inside the Milky Way in our galaxy. And we found all sorts of different planets over the last 20 years. And these planets tell us about the context of our own solar system in the galaxy. So if we were to, for example, rank all of the planets that have been found to date by size, we would learn about how common different planets of different sizes are. And it turns out that if you do that, you would see that the most common type of planet in the Milky Way is a planet between the size of Earth and Neptune. We could also rank planets by different properties, like how long it takes them to orbit their host stars, and we'd learn things about the orbital sculpting of planetary systems. What I'm really interested in doing is ranking planetary systems by age. And if we can do that, then we can actually infer how planetary systems evolve over time. Do young planetary systems look different to old planetary systems? And how do they change? And what is the implication of that for our own solar system? What is the eventual fate of the Earth and the planets orbiting the Sun? Okay, so I mentioned that in this talk I will discuss scales of time in astronomy. And actually, centuries ago, people thought that the stars in the night sky were static, unchanging, and it was the planets that were thought to move. The word planet comes from the Greek for wanderer. So the night sky, the stars, were thought to be stationary and constant. And now we know that that is absolutely not true. The stars really vary on a very, very broad range of timescales. So here is a sort of time axis, and I can put different astronomical phenomena at each one of these scales of time. And these short time scale phenomena are typically referred to as objects that live in the world of time domain astrophysics. So time domain astrophysics is usually used to describe things that we can actually observe changing on human timescales. So things that change from milliseconds up to centuries. This is time domain astrophysics. And it's possible because we have telescopes that are observing stars for these kinds of timescales. But these phenomena, these very long timescale changes in astrophysical objects, like the formation of planets, which happens over millions of years, the evolution of planets, which probably happens over billions of years, and the evolution of our own galaxy, these phenomena are some of the most interesting questions in astrophysics today. And they're interesting because we can't measure them. We can't see these timescales changing. We can't live long enough. And astronomy hasn't been active enough. So in this talk, I will talk about some of these short timescale phenomena, and I will describe how we can use these short timescale changes to learn about these long timescale changes, and to describe how all of these timescales actually interact. Okay, so here's a question. How do you actually tell time in space? Here is a timeline of the Earth and the solar system. So on the left, that's a sort of baby picture of Earth. The Earth and all the planets in our solar system formed in this disk of dust and debris. And the Earth slowly formed out of pebble-sized objects, which joined together to form boulders, which joined together to form planetesimals, etc. After about the first few millions of years to tens of millions of years, the Earth would have been continually bombarded with small asteroids, little pieces of debris left over from planet formation. And the solar system would have been a very dynamical place. So all of the planets in the solar system would have been moving around on their orbits, exchanging angular momentum with each other. It would have been an interesting place to study. And then, a billion years after the formation of Earth, the beginnings of life started to emerge. And from that date until today, the Earth's climate and atmosphere has changed dramatically. And then, of course, we have the evolution of megafauna. I have to show a slide. I have to show a picture of dinosaurs on my slides because I work at the American Museum of Natural History. And eventually, we have cities today. But how do we actually know that the solar system is 4.5 billion years old? And how can we observe changes like this in other planetary systems? Well, let me start with the first question. The sun is the only star that we can measure the age of precisely and accurately. And we do it using meteorites like this one, which we have in the collections at the museum. These meteorites sometimes have calcium aluminium inclusions in them, and you can date them using isotopes. And that's how we know the age of our sun. But we can't do that for the other planetary systems. This is geology. This isn't, really astronomy. So we need to have some other way of measuring the age of planetary systems. So I've described these stages of the Earth and the solar system, but do we see these in nature? Yes. So on the left here, I'm showing some images from ALMA, which is a microwave wavelength array in Chile, and it produces these beautiful images of planet-forming disks. So the gaps that you see in these disks are actually being carved out by planets that are forming. And we found a few of these disks, so a few of these very early planetary systems. We've also found a few planets in this tens of millions of years age range, but not very many. There aren't very many stars that are close to us so that we can detect planets around them that are young. So all of the rest of the planets that we've found fall in this age bin. Basically, after 1 billion years, we don't know the ages of these planets. And it's worse than this, of course, because the universe is older than 4.5 billion years. It's actually almost 14 billion years old. So all of the planets that we've found to date sit in this bin that goes from 1 billion to 14 billion years old, and we don't know how to rank them. So we need to be able to tell time and space. And I asked this question already, and I didn't really answer it again, because meteorite isotopic dating is more geology than astronomy. So how do you tell time and space? How do you tell the ages? How do you measure the ages of planetary systems? I can answer this question by asking, what actually makes a good clock? This is a pretty good clock. I have a friend who he's an antiquarian horologist. He fixes antique clocks. I asked him to send me a photo of his favorite clock, and he sent me this photo. It's a very good clock. I think he knew that I was giving a talk about astronomy because it's got a lunar clock at the top. You can see there's the face of the moon. And okay, this is a great clock. But joking aside, it really is a good clock, because theta, the angle of the hands, changes rapidly over time. So you look at the clock, you want to know what hour it is. It's, 25 to 1. You go and do something, you look back at the clock, and the hour hand has moved. So you can tell the time because theta dot is large. Theta dot for the second and minute hands is larger than it is for the hour hand. So you wouldn't want to try and figure out what minute it is by looking at the hour hand. That would be a bad way to tell the time. You wouldn't be able to measure minutes precisely by looking at the hour hand. So this clock is very well designed for telling the time. We also, over the centuries, have developed other methods for telling the time that are based on the rotation of the Earth. So this is an astrolabe that we have in the collections at the museum. I've got a couple of other astrolabes. There's one on each shelf on either side. You can come up and take a look at them after the talk. And these astrolabes, these use the rotation of the Earth, so you actually sight a star, and because the Earth revolves once every 24 days, the stars move fairly rapidly across the sky, so astrolabes can be used as pretty good clocks. Stars are not good clocks, and this is why. So this is a stellar evolution model that I'm showing. And these two axes, luminosity and temperature, these are two of the sort of fundamental observables of stars. You can really learn a lot about a star if you measure its brightness and its temperature. Now, this brightness axis, this one is really hard. It's really hard to measure the luminosity of a star, its brightness, because this is its intrinsic brightness. So the brightness that it would appear if you were standing right next to it. In order to figure that out, you need to know the distance to the star. There was recently a spacecraft launched called Gaia, which is giving us distances to stars. So all of a sudden, this y-axis is a lot easier to plot. Okay, so this is a model that I'm showing. And this is the sun moving along its evolutionary track. Now, what you see on the far right is the sun coming down this track at a great rate. It's coming down quickly because this is actually caused by the sun contracting onto the main sequence. So it's still forming, it's still contracting from its initial gas cloud that it was born in, and it's decreasing its brightness very rapidly. Then it shoots to the left. Hydrogen burning kicks in at the bottom of this hook. And from the moment hydrogen burning begins, stars become extremely stable. They do not change very much in time. So the sun will be in this tiny region of this diagram for something like 6 billion years. And when stars are here, it's very difficult to measure their ages. After this time, and this is called the main sequence, after this time, stars become red giants, they expand very quickly, their brightnesses go way back up. So when a star is on either of these tracks that shoot up, that's like looking at the second hand. You're able to measure the age of a star very precisely when it's moving rapidly in this space. But when it's on the main sequence, it doesn't change very much in time, so it's like trying to tell the time using the hour hand. So, unfortunately for us, people who are interested in measuring the ages of planets, most planet hosts orbit stars that live here. And that's good for potential life on these planets, because main sequence stars are nice places to live around. They don't change very much over time, but it's bad if you want to measure the ages of these planets. What makes it worse is the fact that, this is just a zoom in of the same plot. What makes it worse is the fact that the observational uncertainties on luminosity and temperature are typically very large. So that makes it even more difficult. Okay, here is another one of these same plots, same axes. This is luminosity again, intrinsic brightness, and temperature. Temperature, incidentally, is a proxy for mass. Low temperature stars are low mass. High temperature stars are high mass. The sun is here. It's that solar symbol, the dot with a circle. And to measure the ages of stars, you measure their luminosity and their temperature, and you place them down on this diagram. And all stars will lie within the regions that are colored, because the laws of physics govern the fact that the stars have to be there. And just to orient you, I'm showing isochrones here, so lines of equal age. I'm not showing stellar evolution tracks anymore. For reference, the sun's stellar evolution track looks like this. So the sun comes in here, it's on the main sequence there, and then it evolves up the red giant branch. So this is how we measure stellar ages. We measure luminosity and temperature, and we try to figure out, based on what color isochrone a star lies on, what its age is. But this is difficult because we have these large measurement uncertainties. And in fact, the temperature change of a star that's over here is only something like 20 Kelvin per billion years. And given that our measurement uncertainties can be as large, or they can be much larger than 50 Kelvin. So it's extremely difficult to measure the ages of these stars. And in fact, most of the time for stars down here, you can't measure their age within the precision of the age of the universe. Okay, so let's come back to this question. What makes a good clock? We want a property of stars that changes rapidly over time. dx by dt must be large. And there is a property of stars that changes rapidly with time. It's their rotation periods. And to infer an age of a star from a rotation period is a science that's called gyrochronology, literally rotation dating. And gyrochronology is really powerful, and I'm going to try to convince you of that. But first of all, how does this work? So stars, they start out with some rotation period that is dictated by whatever the angular momentum of the gas cloud that they collapsed out of was. And then they start hydrogen burning. They're rotating, and if you have a rotating ball of plasma, you often generate a magnetic field. Stars have solar winds. They are continually losing ionized particles. And those ionized particles, because they're moving off of the stellar surface and the star is rotating, they carry angular momentum away from the surface of the star. Now, I mentioned that stars are magnetized. That magnetic field is really important because magnetic fields lock the stellar wind to the surface of the star as it rotates. And so what you're doing by having a magnetic field is effectively increasing your radius. So if you lose a particle of solar wind from your surface, you'll lose some angular momentum, but if you lose it from way out here, you'll lose a lot more angular momentum. And magnetic fields make this lever arm really big. So magnetic fields increase your angular momentum loss rate. What this means is that if you start with a population of stars that all have different rotation periods, the most rapidly rotating stars will have the strongest magnetic fields, and they'll lose angular momentum fastest. The more slowly rotating stars have weaker magnetic fields, they lose angular momentum slowly. And this means that after a certain amount of time, no matter what rotation period a star started with, it will end with the same rotation period. And so you can use its current day rotation period to infer its age. Okay, I have an animation that might make this more clear. So this animation is, it'll start in a second. It's made by Sean Matt, who's at the University of Exeter. This is period on the y-axis, mass on the x-axis. This is rotation period. Slowly rotating things are at the top, rapidly rotating things are at the bottom. These white dots are a group of stars that all have the same age. They're starting from 6 million years old. I'm about to evolve them forwards in time. And what you'll see, first of all, is that the rotation periods will all come down because these stars are still contracting. They're still forming, and so they're spinning up through conservation of angular momentum. Then once they hit the main sequence and the most massive stars hit the main sequence first, you'll see that they start to move back up. Okay, so here the stars are all contracting onto the main sequence. And you'll see in a second that the most massive stars will start to spin down fast because they hit the main sequence first. And then the less massive stars will quickly meet them. They'll quickly spin down and meet the most massive stars. So after a certain amount of time, all you need to know is the rotation period and the mass, and you can infer the age. So the rotation periods of stars move up slowly over time in this plot. Okay, so here's the plot I showed earlier. This is the usual way to measure ages: luminosity and temperature. Measure the luminosity and temperature of a star, and you can measure its age, but it's very imprecise. So what we need is something like a rotation period that gives us a third dimension that allows us to measure an age very precisely. So if I switch the color of age here for rotation period, you can see that it follows age very well. And a star like the Sun will have this evolution track that looks like this. It'll come onto the main sequence, and then it will start to spin down. It'll move across these lines of constant rotation period, so its rotation period will decrease. And so this is how we can measure ages much more precisely. We just add this third dimension to this plot, rotation period, which gives us precision ages. The key thing here is that rotation period change rate, p dot, for the Sun is about 3 days per billion years, which doesn't sound like a lot, but given that the precision with which we can measure rotation periods is much less than a day, it's actually very, very powerful. So this is a big change. So in practice, the way that I measure ages is I use all three of these axes. I still use luminosity, I still use temperature. I get luminosity using Gaia, which gives me distances. And I measure a rotation period for my stars, and I can infer an age. But this has kind of all been story time so far, so let me show you some real data. So this is, again, this is a proxy for luminosity. This is a proxy for temperature, this just color. And this, again, is has the same shape as the previous plot I showed, and the color here is rotation period. If I zoom into the main sequence, you can see that there's kind of a spur coming down above the main sequence. That is binary stars. And we can model binary stars fairly well and remove them from a plot like this. And then what would be left is the main sequence here. And you can see that there's a gradient in color, which corresponds to a gradient in rotation period, which is tracking the gradient in age. So I recently developed a software package called Stardate. I know, it's a great name, which combines all of these things. So Stardate uses Bayesian inference to combine stellar evolution models, classical stellar evolution models, with rotation periods in order to measure very precise ages. Combines all of these things. And just to demonstrate that it works, here is an example of an application of Stardate. So let me explain this plot. There's quite a lot going on. Each one of these curves is a posterior probability density function for a single star. And you see that there are lots of these curves stacked on top of each other. And now the orange curves, by the way, all of these stars are the same age. They're in an open cluster called Persepi, which we know is about 500,000 years old. So these stars should all have the same age. The orange curves show the ages that I infer if I just use luminosity and temperature. and you can see that they're very weakly constrained. For those same stars, if I include their rotation period and measure an age using star date, I get the tight posterior probability density functions. So I measure age with much better precision using rotation period. Okay, so I've talked a lot about measuring ages using stellar rotation periods, but I haven't really discussed how stellar rotation periods are measured. Okay, so this now comes back to the earlier part of my talk where I mentioned time domain astronomy. Time domain astronomy is one of the sort of new hot fields in astrophysics. This is a kind of field that is enabled by large surveys that study the night sky over years, that measure brightness changes. So at the beginning of the talk, I mentioned time domain astronomy. Now let me discuss how time domain astronomy allows us to measure rotation periods. So on here, I have stellar rotation. The rotation periods of stars range from about 1 day in the fastest rotating cases up to about 150 days in the slowest rotating cases. But how do we actually measure the rotation periods of stars? Okay, so we actually do it in exactly the same way that Galileo 400 years ago used to measure the rotation period of the sun. So Galileo used one of the earliest telescopes to look at the sun, and he noticed that there seemed to be dark spots on the surface. And he made drawings of the locations of those spots. And he looked back at the sun the following day, and he noticed that the spots had moved. And he inferred that the whole sun was rotating, and he measured the rotation period of the sun to be 26 days. So we use the same method today. We have much better data, though. So this is the NASA Solar Dynamics Observatory movie of the sun. And you can see this is a time lapse that's really sped up. Normally the sun would rotate once every 26 days, but I didn't think you guys would want to sit here for that long. So these are the magnetic spots moving on the surface of the sun. By tracking the positions of these spots, we infer that the rotation period of the sun is 26 days. And that's great for the sun, but of course, most stars are so far away that we can't resolve features on the surface. We don't see images like this. We see images like this, single pixels, which contain all of that spatial map on just one pixel. But there's a trick that we can use to measure the rotation periods of stars. And this space telescope, Kepler, is one of the reasons why this is possible. So Kepler is a NASA mission. It's a survey telescope. It pointed at one part of the night sky continually for 4 years. And that part of the night sky is about the size of your outstretched hand. So it was a pretty small part of the sky, but it stared continuously for a long time, 4 years. And in that one patch of sky, Kepler monitored about 200,000 stars. And each one of these stars is changing. And there are actually a variety of reasons why the brightnesses of stars change. So this is a movie that I made of Kepler data. I took 500 stars that it observes, and I plotted them down. Whatever their brightness is for real, that is the brightness of the point that I'm plotting. I turned the amplitude of variability up a little bit so that you can see that things are really changing. And this variability is physical. This variability comes about because the stars themselves change in brightness. And why do they change in brightness? It's because they have magnetic spots on their surface. So this is a simulation of a rotating star where I've placed dark spots down on the surface, and then I've integrated over the surface of the star to produce this time series, which we call a light curve. It's how the brightness of the star changes over time. And you can see there's a big dark spot there that just came into view, and there. That big dark spot produces this big dip in the time series. And if you want to measure a rotation period of a star like this, you would do some signal processing on this time series. You might compute a Fourier transform or a Lomsgagel periodogram, or calculate an autocorrelation function, or use a Gaussian process. There are lots of things that you can do to extract a periodic signal from a time series like this. So again, let me show you some real data to convince you that this is real, this is really happening. So this is a real light curve. This is normalized flux. This is relative brightness. And this is time. This isn't actually a Kepler star. This is a TESS star. TESS is a newer space mission than Kepler. Instead of looking at just one small part of the night sky, TESS looked at the whole sky. And it doesn't look for 4 years. It looks for just 27 days. It's also an exoplanet survey mission. So the main purpose of TESS and Kepler is to search for exoplanets. So this is the kind of variability that TESS or Kepler observe, and this is caused by dark spots on the surface of a star rotating into and out of view. This is actually a screen grab. This plot that I'm showing here is a screen grab from an amazing website called test.casino, which I highly recommend you go to. If you hit the Hit Me button on this website, you will be served a random light curve from a star. So actually, it is really interesting to click Hit Me several times to get a sense for how often stars are varying and on what timescales they change. So I recommend that you try that. This was built by Megan Bedell, who is at the Flatiron CCA. She's a postdoc fellow. So I played Hit Me a few times, and I found some other rotation signals like this one and this one. This is a fairly long rotator. I mean, it's still not rotating on long timescales like the sun, because the TESS baseline is only 27 days. At the CCA, we have many tools for measuring stellar rotation periods, and measuring stellar rotation periods is not a straightforward thing to do. I've spent quite a lot of my career figuring out the best way to measure stellar rotation periods, and there are many different ways to do it. We have a suite of software packages that we maintain at the CCA that allow you to measure rotation periods in various ways. These software packages do other things as well as measure stellar rotation periods. Okay. So that's how we measure the rotation periods of stars, and we can use the rotation periods of stars to measure their ages. But what about some of these other time domain phenomena? It turns out that we can use some of these other things to measure the ages of stars as well. Specifically these things. So stellar oscillations I'm not really going to talk about. Stars, there are sound waves that propagate through stars all the time, and a sound wave tells you about the density of an object. So if you measure the frequency of sound waves, you can measure its density, and stellar densities change over time, so that can give you an age. Stellar activity cycles are right at the edge of detectability right now. So the activity cycle of the sun is 11 years. And Kepler's only been staring at the sky for 4 years, and it won't be staring any longer, unfortunately. It's being decommissioned. So we're not, for a long time at least, going to be able to resolve stellar activity cycles, although there are some hints that shorter stellar activity cycles have been seen in Kepler data. But presumably, because stellar activity is a magnetic phenomenon, as is rotation, presumably we can use it to measure the ages of stars. And then there's this other thing, stellar flares. We see flares in our own sun. This is where magnetic flux tubes recombine and an explosion happens on the surface of the sun and wipes out telecommunication satellites. This happens on other stars too, and we see it in test data. Like here's one that I found by just clicking, hit me many times. This is a star that's flaring. You can actually see there's a little bit of a wiggle in this time series, and that is stellar rotation. And on top of the rotation are these spikes, and those are stellar flares. Stellar flares, again, these are magnetic phenomena. And just like rotation periods decay over time, magnetic fields decay over time too. Because if you spin down, your ball of plasma generates a much weaker magnetic field if it's spinning more slowly. So stars that are young, they flare a lot. They flare all the time. This is probably quite a young star. But stars that are older, they flare less often. And we're just starting to see that measuring the flare rates of stars can tell you about their ages. Jim Davenport at the University of Washington's done a lot of work on this. Okay, so I promised you at the beginning of the talk that I was going to explain how different timescales are linked. And I feel like I've done that now. So these short timescale phenomena, these time domain phenomena, can tell you about these long timescale phenomena. Because stellar rotation periods give you stellar ages. Stellar ages give you planet ages. Planets are the same ages as their stars to within a couple of million years. And so we can understand things like planet formation, planet evolution, and even the evolution of the galaxy if we can measure rotation periods. Okay. So what's next? There are a few people working at CCA on trying to improve our techniques for measuring stellar ages and for measuring rotation periods. There's Melissa Ness, who has written some code implementing a technique that uses just linear regression to predict stellar properties. She does it from the light curve. So she can take a light curve and she can predict what the mass or what the temperature of the star is. So we're thinking about ways to develop this and to use it to measure stellar rotation periods. Flatiron CCA fellow Gabriela Contado is working on predicting the properties of stars from their light curves using deep learning. And graduate student Rocio Kuman, who's at CUNY, is working to understand how to measure the ages of the lowest mass stars. And the lowest mass stars are the stars whose ages are most difficult to measure. And this is the reason. I showed this video earlier. I didn't discuss the fact that these low mass stars over here never quite seem to reach that rotational sequence. And that makes them very difficult to date using their rotation periods. So we need alternative methods of measuring the ages of these stars. And the ages of these stars are particularly interesting because TESS is specifically targeting low mass stars, because we know now that low mass stars have a large number of planets. They tend to host multiple planets. So they're a good place to look, especially if you want to characterize the atmospheres of planets. Okay. So looking forward, Kepler, Gaia, and TESS have been launched. All three of these missions are time domain missions. They are time domain surveys. And there are more time domain surveys coming up. WFIRST and Plato are space missions. LSST is a ground-based mission. And all of these missions are going to be contributing more and more to this vast catalogue of stars for which we can measure rotation periods and measure ages. So right now we're at hundreds of thousands of stars. Gaia and LSST might get us to billions of stars. with billions of ages for billions of stars, we are going to be able to figure out the formation history of the Milky Way. We're going to be able to figure out the evolution processes involved with planet formation and planet evolution. Okay. To summarize, we've found all of these planets, these 4,000 planets, and we'd like to rank them in order of age, but that's difficult because it's very difficult. That's hard because it's difficult to measure the ages of stars. They're bad clocks. However, they can be good clocks if we use their rotation periods, and we can measure their rotation periods from Kepler data and TESS data. If we have their rotation periods, we can infer their ages using rotation, but also their brightness and their temperatures. And we can measure their ages within something like 20% precision. In the best cases, we can do better than that. And this is all leading towards us being able to place the planetary systems that we've discovered on a timescale of evolution so that we can maybe one day see things like global climate change on other planets and see things like orbital dynamic sculpting in planetary systems and understand what the final fate of our own planetary system is going to be. Thank you for listening.